All right, so let's go ahead and get started. Um, looks like there's an accident on 60, so maybe some people are coming in. But I've shared the streaming link, so we'll go ahead and get started. Okay, so today's class, I'm going to try to finish it definitely not after lunch. I'll try to finish this either at noon or earlier than noon. Okay, so this is how the three classes are going to be, the next few classes, so that you guys can have some more time for your projects, right? Again, it's a more difficult project. I know people are working on authentication and everything. It's going to take time. So I'm going to try to wrap up the lessons by noon at most. Okay, might be early. We'll see how far we get. Okay. Um, and then the rest of the time would be project until 2 and all that stuff. All right. First of all, my apologies for Thursday. I did get stuck in a production issue. Unfortunately, there's not a good ending. We had to roll back. It was a disaster. So it was a big fail, to be honest. But again, nobody got fired, nobody got hurt, everybody is fine. All right. You hear a lot of success stories, so I did want to share a failure story also. It wasn't something that of course you missed something, but it wasn't like somebody was not up to par or somebody was not doing their job. Everybody did, but in production something does happen, right? It happened. We were working until 9, until around 8:30. We made the decision that we need to go back and fix few things. So we rolled back before it got any bad, right? It happens. Friday came back, fresh start, fixed it. Still not done. We'll probably start the deployment again on Monday and see how it goes. But the fix is there. Again, it happens, and that's the reason. The thing is that how do you deal with it and how do you come up with a solution, right? Everybody knows over there, yes, everybody put in the right time, put in all the effort, it just didn't work out. So it happens. Again, the reason was that, I know people in the classes usually are scared. Hey, if I am hired, if I do this, what's going to happen? Nothing is going to happen, right? It's a good field. Nobody dies. Especially if you are in a medical field. Imagine doctor, nurse says, well, there was a surgery, it didn't go so well. Yeah, that's not a good feeling, right? So, but it's okay. All right. Um, so, coming to today, we are going to start on Arena. Good. All right. You will have time for the projects after lunch. Okay. So we're going to start last week of lecture, and it's going to be on algorithms and data structures. Okay. Let me. So, let's see. So algorithms and data structures. Okay. This is, if you are at ASU undergraduate program for computer science, this is a 6 months course. They teach that in one semester. This is just one of the courses. I'm going to teach you in 3 days. Okay. Actually, not even 3, 2 days. 2.5, depending on because we are going to finish the class early. So I'm going to teach you in at most like 3 days. All right. But here's the thing I want to tell you guys. How many graduates are there in ASU per year for computer science? 200, 300, something like that, right? I will be honest with you, half of the people don't even know algorithm data structures. They are super bad. Like half of the population that are graduating, it's not ASU, it's any computer science program. Half of the people of the class are not familiar, are not comfortable with algorithms and data structures. Okay, so when you're applying for a job, half of the people are gone because they cannot even understand, they cannot even code, or they cannot even explain the basic algorithms and data structures. Okay, but my responsibility, what I'm going to do is I'm going to teach you important ones. I'm going to get to a point that if you understand these, you are good. You are pretty competitive. Okay. Of course, I would like these. This is kind of like one of the favorite topics of engineers who really understand that. Okay. Eventually, I would like you guys in your spare time later on look into these more in depth. They improve your understanding and appreciation of some of the algorithms or how are the programs working. Okay. Um, what we are going to talk about today is we are going to talk about some of the problems and what are the solutions. Now, these are well-defined solutions. Okay. The code that you're going to be looking at is not like hidden. It's already been solved. But what we need to understand is how it has been solved and how did people get to that point. Okay. For example, algorithms. You guys have been doing algorithms whether you know it or not, right? You've been doing your homeworks, you've been doing your activities. Everything is an algorithm. All right. If you've been practicing on lead code or HackerRank, all of those are called algorithms. Okay. Basically, what is an algorithm? It's a step that a computer takes to solve a problem. Okay, so if you're doing your homework, you are writing some code to solve a problem, right? So that's an algorithm. So algorithm is basically just a step that a computer takes. Okay, for the first half, at least for today, and for the next class, we'll look at algorithms, and in the last class, we're going to come back and look at data structures. Okay. All right. So as I was saying, algorithms is a anything that you're trying to solve, you're writing code to solve that problem. And that is considered as an algorithm. It's a series of steps that a computer takes to solve certain thing. Okay? Um, Now not a problem, but computer are literal, right? Like literally you have to spell everything out, otherwise they don't work, right? I don't know if you guys have seen that video. There was a video a dad posted, and he was trying to explain how computers work or how programming works to his kid, and he said, here's bread and here's peanut butter. So consider the dad was like, I'm a computer, tell me how to make a peanut butter sandwich, right? So the kid goes, oh, put peanut butter on the bread. So the dad literally took the jar and put it on top of the bread and said, that's what you said. That is literally how computers work, right? If it is a bad algorithm, if it is not working, it's totally our fault. They will just do what you're telling. Okay? So when it comes to that, what I'm trying to get is that there are algorithms that are efficient and there are algorithms that are not efficient. Okay? Um, I will talk about how do we determine the efficiency of an algorithm. Okay? So algorithms can be efficient, can be non-efficient, and they are not efficient at all. Okay? Now, when we are solving anything, the first approach should be that you write an algorithm, whatever comes to your mind, how inefficient that algorithm is. It does not matter. Okay, that's always the first solution. So the algorithms that we are going to look at today is the first step. Those are the solutions that people came up with at first, but again they realize it's highly inefficient. It's not going to work, and then we slowly progress to some of the algorithms that are extremely efficient. Okay. Um, for example, we will start with some search algorithms. Okay, what does that mean? It means that you are given a list of elements and you want to search something. Okay, the examples that we are going to look at, you will think that these are like small examples, but these are the algorithms that are actually being used in searching. Okay, companies use these algorithms to conduct some of the searches and everything. But I want to compress that to the understanding. That's why we're going to look at some simpler examples, but they can be scaled to anything else. Okay, so in our case, we will look at algorithms, search algorithms. For example, we will have an array because that's the list that we have learned. So we can look at our search algorithms first. So you will be given a list of numbers, and you need to find some number in that list. Simple. Okay. So for example, you have a list of numbers. Let's put in some numbers: 3, 35, 2, 45, 90, 1. Okay. We'll look at some examples. We'll start small and then we'll see how these algorithms scale. Okay. So this is a simple array, right? And the purpose of this is you search something in that array. For example, I say search and tell me if the number 2 exists in this array. Okay? And it does. We as humans can look at it and be like, yeah, there's it is, and it's on index number 012. Okay? So my number 2 that I'm searching for, it's at index number 2. Right? I change that criteria. I say I want to find out number 45. Right? That's at index number 3. I can look at it and I can say. Okay? Now, how do you translate that? How do you translate your thinking into a computer program? How do you tell your computer to find this number? Right? Of course, the program cannot see this and be like, oh, this is the number that you're looking for. So we have to write some code, right? That's what an algorithm is, right? So we have to write some code that our computer program can look at this array and find out exactly the number that we are looking for. So we are looking for 2. It can scan this array and tell me if the number 2 exists in this array or not. Okay? So the code that you write, this is the problem, right? The code that you write for this problem would become an algorithm. All right? It's literally just the steps to come to the conclusion, to come to the solution. Okay? Is that clear? All right? Everybody understand what an algorithm is? Right? The next step is efficiency. How do we measure if this algorithm is good or bad, is fast or slow? Okay? So there are 2 things we use to determine the efficiency. It's called time and space. Okay? It's called time and space. These are the 2 things that we use to find out if the algorithm is efficient or not. Okay? Let's start with space. Space just means literally how much memory your algorithm is going to take. Okay? So let's suppose if I have this array, this is taking up some space, right? It's taking up some space because literally it's in my code. All right? If I have a second array, this means I'm taking some more space, right? Any variable that you declare, that's taking more space. So if I have a second array in my code, this means I'm using a little bit more space, right? So the more space the algorithm takes, it's considered less efficient, all right? But we are not going to worry about space right now in this class. The reason is space is becoming less of a problem now, especially with our computers now. We have a lot of memory and space, so it's less of a problem. Okay, but when you're determining the efficiency of a algorithm, time and space both are considered. Okay, but when you go out, when you're interviewing, you will see that people are less concerned about the space. They are more concerned about the time. The algorithm, the solution that you come up with, they will definitely ask you about the time. Okay, so let's concentrate on what time means. Time means how quick your algorithm can spit out the solution. Like if I say I want to find number 2 in my array, how much time is it going to take to return the result and say whether 2 is present or not? Okay, is it going to take 1 second, 2 seconds, 3 seconds, 5 seconds? That's what time is. Okay, now understand that 1 second in computer is a lot, right? If your algorithm is running for 1 second, it's kind of considered inefficient, to be honest, right? In computer terms, 1 second is a lot of time, right? We'll see. There's no like optimal time. There are some things that take more than 1 second, of course, but a second in computer terms is a lot of time. Okay. All right. So that's the time thing. So time means how much time does your algorithm takes to run through the code, run through the steps. Okay. And how do we increase the time? the more steps that you have in your algorithm, the more time it's going to take. Okay? So if you have one step in your algorithm versus if you have 100 steps, is going to take, the 100 steps is going to take more time. Okay? Now an algorithm is, remember, what is it? It executes everything a step. All right? The more steps you have, the more time it's going to take to execute that algorithm. Okay? So that's how we determine the time. Right? Now what do I mean by step? Step is every line of code. All right, every line of code that is executed by a program is considered a step. All right. For example, variable declaration, that's a step. You have to swap some numbers, that's a step. You have to assign some numbers to a different variable, that's a step also. If you have a for loop, that's a step itself. Okay. Now here's the important part. If you have a for loop, and that for loop runs for 100 times. You have a for loop which says starts from 0 to 100. How many steps is that your program is taking? 100 and whatever the everything else is. So your lines of code for loop would be like 3. For some one statement and then end, right? 3 lines of code. But the number of steps the computer has to take is 100 plus whatever you have, right? So always remember, when you have a for loop, and every time that for loop is running, that's a step. So if you have a for loop for 1000 numbers, it's running 1000 steps. Okay, plus whatever you have. Okay, is that clear? Everybody understand? Okay. Now, these time and space efficiency, they are approximated. They're not exact, right? So what do I mean by that? For example, when you have steps like variable declaration, assignment, we kind of ignore those steps, right? We only consider the steps that are more important, that are going to affect the algorithm. For example, the for loop. That is the biggest time determination of the time. Okay, if you have 1000 elements and you're running through them, running through that array for 1000 times, that is more prominent than just a declaration or those kind of steps. Okay, so you can approximate that, and we come up with a approximate efficiency by looking at bigger pieces of the program. For example, our for loops, for example, our while. Okay, for loops, while loops, those are big ones. Okay, those are the ones that actually determine your efficiency of the program. And the reason is, for example, if I tell you to search some number, what do you think would be the algorithm for that? High level. If I say, okay, this, I'm going to give you an array, you have to write a function. Okay, what does a function do? In my function, I'm going to pass you this number. I'm going to pass you the number that you want to search for. Okay, in the array, if the number is present, you tell me true. If it's not there, just say false. What would be the high level algorithm for this? For loop, right? What does the for loop do, Chris, in this case?
Steps through each array index and checks the number.
Okay, you guys see what he's saying? He's saying that he's going to create a for loop which is going through step through each one of these numbers, and is going to search for the number that you're looking for. Going to have a for loop which is going to run from 0 to length -1, length of the array -1, because of the index number. Okay, and then what are you going to do? You are going to write an if statement, and then you're going to check the number to be searched is equal to my array dot, let's say, I. Okay, if this is true, this means you have found the number. You can do a break, return true, or whatever. Okay, pseudo high level code. Okay, does everybody understand this algorithm, the search one? Any questions on this? Because the next one, I'm going to talk about this in more detail, and it's not going to make sense if you don't understand this one. So what we are doing is, we have a for loop. We are stepping through each one of these elements and trying to match if the number is present. Okay? Any questions? Good? Okay. So when we consider the efficiency of the algorithm, I said we are going to consider time. Right? So we'll concentrate on the time. The next thing is we find out what is the best case scenario, what is the average case scenario, and what is the worst case scenario of an algorithm. For example, what is the best case scenario for this algorithm? The best case would be if I'm trying to find the number 3, right? It's going to start, find the number, and that's it. That's the best case that can happen to this algorithm. That the element that you're trying to find is the first element in the array. Okay? That's called the best case scenario. The worst case is if I try to find the number 1. Why is it worst case? Because it has to start here, then here, then go here, then go here, then go here, then go here, and then find it. So that's considered the worst case because it had to parse through every single element of the array, right? Best case, if you try to find the first one. The worst case, if you're trying to find the last one in this scenario, right? Different algorithms have different scenarios. And the average case would be if I'm trying to find something that is right in the middle. For example, 2 or 45, that would be considered like an average case. Okay, so best case, average case, and worst case. Okay, any questions on these 3 things? Okay, so when we are determining the efficiency of the algorithm, we concentrate on the worst case, right? You will see when we talk about efficiency, people are always by default considering how your algorithm is going to work in the worst case. In this case, the worst case would be if I'm trying to find the number 1, right? So when we try to talk about how efficient my algorithm is, the consideration is how my algorithm is going to perform in the worst case scenario, which is finding number 1. Okay? Now in this case, let's talk about the worst case now. So worst case is if it's the last element of the array, right? Now, right now I have like 6 elements. If I scale this to 100, the worst case would be the last element, the 100th element, right? If I scale that to 1000, the worst case for this one would be the 1000 element, right? If I have 1000 elements, numbers in my array, and I'm trying to find the worst case would be the 999th element, which would be the last element in my array. Okay? So if we generalize this, and this is the length of the array, let's say n, right? This is my length of the array, right? So in my worst case, I have to go through each single element, which is the length of my array. All right? So when we talk about efficiency of this algorithm, you will hear we say that this algorithm has an efficiency of O n. Okay, it's the letter O, not 0n. Okay, and why is it O n? We call this because as the number of elements grow, your worst case also grows, right? If you have 100 elements, the worst case would be the 100th element, right? If I have 1000 elements, then the worst case would be 1000, right? So if I have, depending on the number of elements in my array, if you approximate that to n, generally you will see the letter n is used for the length of the array, right? That would be the worst case for my array. Like if I have number of n elements, then my worst case would be the nth element if I'm trying to find the last element. Okay? Well, if you want to be exact, the right would be n minus 1 actually, because n is the length of the array and the last element is n minus 1, right? If your length of the array is 10, then the last element is index number 9, which is 1 less than n minus 1. 1 less than n, right? But since this is all approximation, this single 1 digit doesn't really matter in the big scheme of things. So if you have like 1 million numbers in your array, 1 million minus 1 wouldn't make any less efficient or more efficient. So that's why we kind of drop these numbers and we kind of come to that approximation and say this element has an efficiency of 0n or on. Okay, now what does O mean? O is a notation called big O. It's called big O notation. Right? We'll talk about big O a little bit more in later on. Just to give you an introduction, this scheme of things, this trying to find out the efficiency of an algorithm is called big O. It's called big O notation, and the notation is starts with the O, parentheses, and then some kind of a formula. Right now, in this case, it's n because that's what we determined. We said the worst case for this is the last element of the array, and that's what we put in our big O notation. Okay. Now, why am I talking about big O and all that stuff? You will see when you are interviewing and people ask you to write an algorithm, most definitely towards the end, they will ask you, can you tell me what is the efficiency of your program? Basically, they are trying to find out if you can write this notation over here, the big O notation. Can you come up with this? Okay? So I want you guys to be prepared. That's why I'm going to be talking about this, so that you guys can write your algorithms and find out the big O, the efficiency of that algorithms on your own. Okay, I'll guide you through few, and you will see generally there are some fixed big O notations, and usually it's one of them. There are like 5 or 6 ones. So you need to find out which one of them is the one that applies to your algorithm. Okay, so one of them is ON. So if you have a for loop, a single for loop, and you're looping through some array, all right? Doesn't matter if you're searching, doesn't matter what your solution is. Okay, it could be interpreted in different ways. Right now, it's a simple one where you have an array, and I'm saying, hey, search for this number. Okay, so I have a single for loop, and I'm looping through the whole array. And my worst case is if the element is the last element of the array. So my big O or my efficiency of this algorithm is ON. Okay. So generally speaking, if you have a for loop and you find out that in worst case you're going to go through the whole for loop, then it's ON to be safe. Okay. So if you come up with an algorithm and they're asking, hey, you have a for loop, what would be the worst case or what's the efficiency? ON is pretty much the starting point. Okay, for a single loop. If you have more than one, we'll see what happens. Yes.
So would it be bad to say O and n minus 1? Is that kind of
Yeah, it just redundant. Yeah, we can say O n minus 1, but eventually the interviewer would be just looking for ON because we approximate. And I'll show you there are fixed ones that the ON is one of them. So anything that is close to this, even if you find out it's like n minus 2 or n minus 3, you will not say it's O of n minus 2. You will just say O of n, just approximation. Because in a big scheme of things, the negative number doesn't really mean anything. Right? If you have an array of 10 elements, makes difference. But when we are talking about the worst case scenarios and all this efficiency, we are talking like millions of elements in an array. That's how you need to think. That if my algorithm has million of these numbers, how is it going to perform? It's going to perform in this case. Okay? So this means as my array grows, the time for this algorithm to run is growing as well, right? If I have 10 elements, it's going to take this much time, right? To go through all the 10 elements, right? If I have 1,000, grows more. If I have 1 million, kind of grows over. So as my array grows, the time for this algorithm also grows, okay? This is considered one of the most inefficient algorithms. If you have an algorithm that has a ON, it's kind of considered very inefficient. And the reason is, as your data grows, the time to complete that execution is also growing, right? It is significantly growing. So if you have like 1 million things to search for, it's going to take that much of a time. Okay. Now again, we are not talking time about like seconds or anything. It's all approximation. It's relative. It's going to take a lot more time when your data grows. Okay. So you will see algorithm that have a ON. There's an alternative solution. There's a efficient solution that is already out there, but usually the algorithms with this inefficiency are not really used in like big scale, right? They're not efficient. You cannot expect this to run if you have a data set of like million elements. It's going to take a lot of time. Okay. So that's why this ON is kind of considered a little bit inefficient. All right. Any questions? Okay. Now, for example, if you were, we'll consider that this was the question that was asked in your interview. Okay. I'm going to give you an array of elements. Go ahead and search. How would you write this code? And you come up with this code, right? Highly inefficient, but that's okay. All right. I at a senior level will be asked the same question, right? But where's the division? Where's the like you would be like, well, if you are also going to get this asked and I'm also going to get asked the same question, it's kind of unfair, right? But it's not unfair. For you guys as a junior developer, if you are given this question and you come up with this solution, it's expected, right? Well, the interviewer will be like, yeah, okay, no experience, that's okay. And the next question would be, hey, can you make it more efficient? And the interviewer is going to guide you to some more efficient solution. Okay? But the expectation is that you are able to whiteboard this solution, this inefficient solution. And it's not true just for this case. Any solution that they're looking for, it is expected by default as a junior programmer, you're going to come up with the most inefficient solution, which is okay, right? And the questionnaires, the interviewer is prepared. The next set of questions are, how do you make it more efficient? Okay? They're going to guide you. They're going to say, hey, what is the big O notation for this one? You're going to say ON. They'll say, oh, do you think this is efficient? No, it's not because I studied and I know ON is not good. All right, let's try to find out a better way to do it, right? And they will guide you. That's okay. In my case, if I write this algorithm first time, I'm already rejected, right? I at a senior level cannot even write this algorithm on the board, right? Expectation from my level is that I'm going to write the efficient algorithm. How do I tackle this question? I'm allowed to talk about this inefficient solution. When I come across this question, the expectation is I'm going to say, okay, right off the bat, I can write a for loop. It's going to go through it. It's going to search for it, and I will get my result. But it's highly inefficient. That's what I would say. Okay, and the interviewer is like, okay, they kind of warmed up. They're like, okay, well, at least the guy knows something. But I cannot waste their time in writing this first and then trying to come to the efficient solution. Okay, at my level, the expectation is that I'm going to talk about the inefficient solution. Don't write it, right? And then I'm going to eventually write the code that is efficient, and we'll talk about that. Okay, but at your level, right now, the expectation is you're going to come up with an inefficient solution, right? The expectation is that you're going to write this up. If you cannot write this algorithm, that's already kind of done deal. Okay, you're not going to proceed. So the expectation is you're going to come up. So if you're writing algorithms and you think they are inefficient, that's okay, right? At least you're getting the result, right? If you practice on lead code or HackerRank, some of you might have run into this issue, some of you might not have, depending on how efficient your solutions have. I have run into these issues that if I write an algorithm and they also have a timer at the back end, they are actually measuring the time complexity of your algorithm. It's actually even less than seconds, probably less than a second or something. So if your program takes more time to complete, you will get that error on the website saying it's too inefficient. Okay, I ran into that issue. So this means that there is a from among the inefficient solutions, there is still an inefficient solution that is out there that you can write. That's what it means. Okay, the solution that you came up with, or for example, I did, and it said, oh, it took too much time to complete this, so please go back and redo it. This means that I was not able to even write the least inefficient solution. Okay, that's what it means. So you might run into this issue when you are doing gate code and all those questions. They are measuring the time complexity. Okay, of course they're not measuring the time complexity of like crazy like a less one, but this is acceptable. But if it takes more time, you will get that error as well. Okay. All right, is everybody clear? Understand? Okay. The goal as a junior developer is that you are able to at least complete that. It doesn't mean it is efficient or not. Efficiency is the next step. The first step is you are able to write this code. Okay, at my level, when you guys grow senior, the expectation would be that you understand this solution very easily and you know it is inefficient, and then you start with a efficient solution. That's the expectation. What is one? Right, we'll take a look at what is efficient for this one. Okay, any questions? Okay, before we look at the efficient solution, let's look at the activity. You don't have to this activity. So the first one is benchmark. Benchmark activity is actually measuring the time that it takes for this algorithm. All right. Within the code, it is generating an array of certain length. The length you can specify. All right. We'll start with a length of like 100 or 10, and then it goes ahead and measures the time it's taking to run through that array. Okay. For let's see this one. Let's look at this one. Okay. Again, you don't have to worry about the code and everything as much. Benchmark is a Node.js library that you can use to measure the time it takes for an algorithm to run. Okay. All of this is just a setup, and you can take a look at it at any other time. The more important is this line number 17 to 23. Okay. This is where you put the algorithm that you're trying to find out how good it is, right? How much time it is going to take. Okay, so if you see, this algorithm that we talked about is called linear search. Okay, why is it called linear search? Because it is going one by one by one. It's like a linear and a straight line search. That's why it's called linear search. Okay, highly inefficient, doesn't work for use cases with a lot more data, and we'll take a look at it. Okay, so if you run this code, do a npm I, it will install the benchmark library. All this setup is done. We don't have to worry about that. What we will do is we're going to run this. This is examples in your search. And right now, you see the length over here. We're going to reduce this length. We're going to say the length of the array is 100 numbers. Okay. Mention this, and then if you see the next line, number 8 is a generate method. We can go and take a look at it. Generate method basically renders a random number of arrays of length 100, and this random value is picking one number from that, and that's the number you're trying to search. Okay, that's all it does. Okay, so we'll start with a length of 100, and if you run this, starting. Okay, so this is the time that it took to complete this search. Not even a second. It's like 1/8 of a second. Okay, still this is considered an inefficient algorithm, right? So let's increase the length to 1000. This time I have 1000 elements in my array. So you will notice that it kind of starts getting slower and slower as the length of the array increases. So a little bit slower. Let's see, add one more 0. Okay. Let's add 0. Let's see how far you can take this for it to break. Okay, so it's now coming closer. From the 8, it's now down to you can actually see the numbers in one screen. So it's kind of getting slower as the length of the array increases. Let's add one more 0. Okay, one more. Okay, so the time you see is kind of increasing as the number of the elements grow. Eventually you will see it will run out of memory. It's taking too much space, and that was the breaking point. Okay. Eventually, you will see this error. It's not anything crazy. We'll fix this error. But basically, every program in your Node.js gets allocated some space. I think it's like 2 MB. So if you use up that memory, it says that you are out of memory for this program. You can't use anymore, and it will give this kind of error. So you see the heap error and everything. This is all related to memory. So your program was allocated, I think, like 2 MB space by default, and the algorithm was inefficient. It ran for so long, and basically it used up all the memory, all the space that it was getting. Okay, you can fix this for now. There is and you don't have to. I can select this out. It's when you are running a node program, there is a command you can add which says max old space size and then mention a size. Over here, I'm saying is increase the size from 2 MB to 4 MB. Okay, this is all in bytes. That's why you will see 4096, but it roughly translates to 4 MB of data. Okay, so you're saying increase the space for this program to 4 MB and then go ahead and run this program again. Okay. Let's see, this should not fail now. It should at least not run, but it's going to take a lot more time to complete that process. Okay, so you see it's kind of coming closer to 1 second. Eventually, if you keep increasing, it will come to that point, right? As I said, 1 second in a computer term is a long period of time, right? You see in an element of 100, when my size was 100, it took only like uh, 1/8 of a second, right? So this is what we are trying to determine. If my algorithm can run on big data set, and that's where the efficiency comes in. So this we can safely say this is an inefficient algorithm because as the space grows, it's taking even more time to compute that. Okay, and what is the notation? We said this is the efficiency or the big O of this algorithm is ON. Okay. All right. Any questions before we take a look at the more efficient solution? Good. All right. So, a more efficient solution, the algorithm is called binary search. Anybody heard of the binary search algorithm? It's called binary search. So let's do this. Called binary search. Let's take 5 minutes. Just Google the word binary search and see if you can find out the code for it and see how it works. And I'll explain this in detail. Binary search. You will come across some code. Um, don't worry about the code too much. See if you can understand the logic. How does binary search work? And then we'll go 5 minutes. We'll go over and see how binary search works. spoiler.
Yeah, what's the cost of sorting the list
All right. Other than the sorting and everything, let's forget about sorting. How does binary search work? No, don't worry about the sort. What is it? You have to divide it in half. Okay. What does that do afterwards?
And if whatever you're looking for is less than the first half,
Ah,
or it's more than the first half, you're just looking for those halves.
yeah. Excellent.
In
So,
those halves.
and what?
In those halves.
In those house. Okay. Oh, that's a nice way to say in those house. All right. So how does binary search work? Binary means 1 or 0 or 2. Okay. What binary search does is it divides the array into half. Okay, until it finds that element. For example, if I'm trying to find, let's say, 183. Okay, I want to search 103. What would linear search do? It is going to go across the. Let's find it difficult. Let's do 310. Okay, for linear search, it's going to go through this. So binary search works. For example, if you have a book, let's say you have a dictionary, right? You're trying to find meaning of a word, right? For example, you're trying to find what does data structure mean. Okay, so how do you start the search? Let's suppose you open the book at just in the middle, right? If the page opens to, let's say, letter F, you know you want to go back, right? You won't go ahead and search for the word data structure in the dictionary ahead. What do you know? You would go back because F, you're saying, oh, the word D is going to, the letter D is going to be behind, right? So you will flip the pages to the back. That's exactly how binary search works, right? How does it work? If you're trying to find the word, find the number 310, what it does is the first thing it does, it divides the array in the middle. Okay. In this case, the middle would be how many elements are there? 3, 6, 9. So this would be okay. It divides the array in the middle, and then finds out what is the number that is in the middle. So let's suppose the middle is 222. Is that correct? Okay. So we are trying to find the lower number. Okay. So it looks at the middle number, 222. It compares 222 with the number that you're trying to search, and then says whether this number is going to be less than over here or is it going to be over here. Yes.
In that sense, are you assuming that it's sorted in a specific direction, whether it's ascending?
You guys are like going ahead so fast. Yes, we'll come to that. Yeah. That was my big question. That what is the downside of this algorithm? Yes. So since everybody's talking about it, this algorithm only works if the list is sorted. Okay. Let's get this out of the way. Is everybody happy now? I'm just joking. Okay. So this algorithm works on only on sorted list, right? We'll come to that. The next question would be, well, how is it more efficient? Why don't I just use linear search? Because if you remember, for linear search, the sorting is not a requirement, right? You can put anything unsorted list and it will still work, right? So we'll talk about efficiency. Why is this more efficient than linear search, even though I have to have a sorted list? Okay, we'll talk about that. But yes, the point is that for binary search, the list has to be sorted, right? It does not work in an unsorted list. It cannot. Okay. So if I'm trying to find 310, I 100% knows that the 310, since this is greater, is going to be somewhere over here. Either it's going to be here or not at all. Okay. So I'm going to discard this whole list over here. Okay, and then I'm going to start my search from here to the end of It's of course not this, otherwise I would have found this number. Right? In the next step, now my remaining array, this is gone. I'm going to do the same thing. I'm going to divide this remaining array in half again. Okay? In this case, it's an even number, so it goes to the you add them up, divide by 2, and take the floor, basically the lower of the half. All right. So right now there are 4, so 4 divided by 2 would be 2, so that's why it comes over here. Okay. So anyway, we have again divided our remaining array into 2 parts. So this is the midpoint. Okay. Now what it does is it checks, is the number that you're searching going to be less than this, greater than this, so it's going to be over here, or is it equal? If it is equal, this means you have found the result, and it will say, okay, this is the answer. All right. How many steps did it take? Now remember, if you were doing this linear search, it's going to take 1, 2, 3, 4, 5, 6, 7 steps. Okay. In binary search, we were able to get to that result in like 2 steps, maybe. Right? You did the half, and then you search for this one, so that's 1 step. Then you came over here, and then you did the half again, and you matched this. Luckily, this was there. So from 7 to 2 or maybe 3 steps. Okay, the number of steps were halved. Okay, now you extend this to a bigger data set for like million. The same thing is going to divide it into 2. So the time that linear search is taking, it's almost taking half or less of that time to come to the same conclusion. Okay, for example, if you were searching for 327, the same thing stops over here. It's going to check if it is greater or less than. Greater than, so it's going to discard this whole part again. It's going to come over here and then try to find this one. Again, by dividing the array into 2 parts. That's why it's called binary. It's dividing the array into smaller halves until it gets to the last element, or the element that you're trying to find, or it determines the element is not present. For example, if you search for 399, it's not over there. It's going to keep doing half, 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 half by the point it reaches the end point, and it's going to say, well, that's the end of the array, so this means the element does not exist. Okay? All right, this is a really good website, and we'll follow this again so that you can see, and I'll share this link as well. What it does is it goes through the whole animation to try to show you how the algorithm is actually working. For example, this is a list, it's a small, so like 31 elements. Oh, 32. And if I'm trying to search, let's say 917. Okay, I will say 917. And let's do binary search. Let's do a pause. Okay, the first step is it takes the starting point and an end point of the array, right? And then divides it into 2. Divides it into 2 halves. So how does it divide? It takes the first index, the last one, add them up, and divide it by 2. That would be the midpoint. So the first step is you have to determine the midpoint of the array. So what's going to be the midpoint of this one? This would be 31 plus 0, 31 divided by 2. So it would be 15.5. Take the lower number, 15. Okay, it takes the lower of the whatever the calculation is. Because midpoint doesn't matter. It's going to be 15 or 16. It will still work. Okay, in this case, it is considering the lower of the 2 numbers. Okay, so the midpoint is going to be 15. So let's do step forward. And that's my midpoint. Okay, now my midpoint has a value of 534. It goes ahead and looks what the value is, and the number that we're trying to search is 917. So it makes a comparison and sees that is 917 greater or less than or equal to. Okay, if it is equal to the number, the midpoint, this means we have found a result. But in this case, it's not. So next thing it says is it less than or greater than? It's greater than. So it's going to discard this whole array. The number has to be somewhere over here in the next half. Okay, what does it do? It finds out it is greater than, so it moves the pointer, the starting pointer, to this half. right? It discarded this whole array. The starting point is now moved to midpoint plus 1. It is checking against what?
It's checking if it's equal to the.
Yes, the first thing it checks if it is equal. Otherwise, if it is equal, that's the number that we are searching for. And then it says, okay, if it's not equal, this means that's not the result. So I need to continue my search. So do I need to search in this half or do I need to search in this half? Okay, so I need to search in the next half because the number is greater. So we move the starting point, we call these pointers. Okay, we move the starting pointer to the next one of this half. Okay, same thing, find the midpoint, so 16 plus 31 divided by 2 and the lower of those two comes to 23. Okay, again these are index numbers and these are the actual values. Okay, so this is the midpoint now, the same algorithm again. So it's going to find out if the value at the midpoint is equal to the number that I'm searching for. No. Okay, so that's out. Now, is it greater than or less than? Still greater than, so I need to search, I need to discard this whole array and I need to move over here. Okay, so it goes ahead and it will move the initial pointer to number 24. Okay, now does the same thing. 24 plus 31 divided by 2 and the lower of the result, that would be our next midpoint. Okay, now it's going to check if the number that you're trying to search for is equal to the midpoint. It is, and that's the answer. So it's going to stop over here and it's going to say the element was found at index number 27. Okay, one more time. Let's go. One more time. Okay. Let's search for. What do you want to search for, Simon? Let me refresh this. So, okay. Which one was that? 876. All right. So we're going to search for 876. Oops. Okay, we'll do a binary search and we'll take a pause over here. Okay. We're trying to search for 876. So start with the same thing. First index and the last index, right? So 0, 31 divided by 2 comes down to 15. So it's going to come back to 15. Okay. So that's my midpoint. Checks and sees if the value, if the element at the midpoint is equal to the number that I'm searching for. It's not. So I need to keep searching. Now, do I need to search in this half or this half? It's greater than the midpoint. This means I need to search in this half. All right, so it's going to move the pointer to my starting point to midpoint plus 1. Okay, now midpoint is going to determine the midpoint of this to this. So 16 plus 31 divided by 2 and the lower of the number. So it's going to be 23. Right, so at 23, the midpoint is going to run again. It's going to see if this is equal to 876. No, keep searching. Now, do I need to search in this half or this half? This half, because the number that I'm trying to search is greater. Okay, so it moves the pointer over here. Right? Find the midpoint again. It comes down to 27. It's going to check 876 is equal to this. No. Okay. Is it going to be over here or over here? It's going to be less than. Okay, so I need to discard this array over here now, right? Now my starting position is going to remain the same. Why? Because it's under consideration. My endpoint is now going to move to 1 less than whatever the midpoint was. Again, why? Because I want to discard this array. I don't want to look into this array. The reason is the number that I'm trying to search is actually less than the midpoint. Right? So my end, which is 31, is going to move to 26. Okay? Now it's going to find the midpoint, is going to be 25. And then it's going to check if the midpoint, the value of the midpoint is equal to the number that I'm searching for. It is. Then it's going to say this is the element that I have found at number 25. Okay? So, couple of things. The midpoint is always going to be the search result. I hope you guys see that, right? If your midpoint is, if you are not able to find a value at your midpoint, this means the number doesn't exist. It stops at the midpoint. Every time you are at the midpoint, it's checking to see if it matches the number that you are trying to search. If it doesn't, then it moves a pointer. But eventually, if the value exists in your data set, it has to be on the midpoint. Right? Do you guys see that? It is going to be at the midpoint. Right? If it does not exist and um, you cross the end and the start, you will see that's when the algorithm stops. So let's go back and try to search something that does not exist. So let's suppose I'm trying to search for number 799. Okay, it does not exist in my list. Okay, finds, ooh, that was too, 799, binary search, pause. Okay, so it's going to find the midpoint as usual, and it's going to find out should be greater. So it's going to get the second half out of it. Okay, comes over here, finds the midpoint, 23. Is going to be on this side of the array. So it's going to move the 16 to 24. Okay, finds the midpoint, 784. It's going to be greater, not equal to this, so I need to find in the next array, in this case. Okay, now it's going to find the midpoint. It's going to land on 29 because if you divide by this, the lower number would come to 29. Okay, now it's going to find out if this is equal to no, it has to go forward, which is going to move the initial counter from 28 to 30. Okay, it's going to add them up, try to find a midpoint. The midpoint is going to be 30, right? 30 plus 31 divided by 2, and the lower number is 30. Okay, so your midpoint and your starting point are the same. Okay, it's going to look for that midpoint, is going to find out if this is equal to, it's not, it cannot go back any further, right? Because you have already discarded this element, it cannot be over here, right? If this does not match, it says the element actually does not match. So it crosses over, but you're not going to actually do anything over here. And the reason is your end has crossed over into your starting point. And that should not happen. That is your breaking condition. If that happens, if you're starting and your end cross each other, this means the element is not there. Okay, that's your stopping condition. So it's going to stop here and say element not found. Okay, so a couple of things over here. The stopping condition is you're trying to search for an element. Your starting index should always be less than your end index. Okay, if your starting index becomes greater than your ending index, this means you have crossed and the element is not there. That's your stopping condition. If you don't have this condition, it's going to keep running forever and ever and ever. Okay, so that's the stopping condition. That your starting index, which is going to be this one, your ending index is this one. We are kind of bringing this over here, and we are increasing this, but it should never cross. These both should not cross each other. If they cross, you have to put a check over there and say, if they have crossed, this means I have scanned the whole array, the element is not there, so I'm going to stop my execution. It's not there. Okay? Any questions? Good? All right. Anybody wants to whiteboard this algorithm? It's not as difficult as it seems. The hint is all. I will keep this up as well. Okay. Then go ahead and write it out. Right. It's right there. Right. I know. That's what you will say. It's right there. Well, go ahead and write it out. Then if it's there. Anyone wants to practice? Just a for loop and well, a while loop and your if conditions. So you're starting your array. You are given an array of numbers. That's the assumption. So you can say you have a function. You're getting some array inside it. Okay. So you are going to start the array, find out the starting point and the end point, then find the midpoint, and do some if conditions. Anyone? Somebody? Oh, all right. And you can walk us through, and we'll as a class we'll help. And
Well, the low point would be 0,
low point would be 0. Okay.
and the high point would be -1, or
Okay.
just -1.
Yeah.
And then I'm using a while loop.
Okay. What does your while loop do?
So while the low point is less than or equal to the high point.
Oh, you guys see that? So this is that crossing condition I was starting. So right now it's 0 and the length of the array, which is, let's suppose, 50, right? So she's checking if 0 is less than 50. Okay, you can keep going. So your low point should always be less than your high point. Okay?
I don't know if this would go inside or outside the while loop.
It's going to be inside. Everything is going to be inside. Okay?
So the midpoint
Okay?
is going to be low plus high.
Okay? Okay, yeah, that's good. So we'll determine divide by 2 and it gives us the lower of the two numbers. Okay, we'll simplify that. Okay, so example, if you add 0, 31 divided by 2, it will say 15. Yeah, yeah, that's fine. So we'll say this is giving you the lower one. Okay, so I have a midpoint which is, okay, so I have the high, end, and midpoint. Now what happens?
So then if midpoint
Uh-huh.
equals whatever you're saying,
Okay, let's suppose it's inside a variable called num.
then you return that index.
All right, so here's the comparison. So what is mid? Mid is the index number, and the num has actual value.
Right.
Okay.
So
Hmm?
oh, index
If it is what?
index with number is equal to, we don't know the index of
If it's equal,
So what is mid? What is mid telling?
that. So
It's the index number, right? It's this number. So you have an array. How do you find the element inside an array if you have an index number? Yeah, that's it. Yeah. So array and mid, and this will give you the element. Okay. Yeah, yeah. So you're comparing it to, so the number is actual element inside, and mid gives you the index number. So you're saying, oh, go to that and find. Okay, yeah,
and we would return
okay, yeah. So we have found our result. That's one condition. Excellent.
if it's less than 0,
Okay,
then the high point
So, um, so your array midpoint is less than the number. So this is my midpoint, and I have found out that this number is less than the number that I'm trying to search. So this means I need to search over here, right? I need to search on this part. Okay, let's refresh this. And so let's suppose I'm trying to search for 246. Okay, so that's your first condition. Um, you did that. It comes over here, right? You have the midpoint. You confirm it's not the result, right? It is going to be less than. So my midpoint over here. Oh, you have the condition this way. Okay. So my midpoint is less than the number. Let's search for something that is in the. I mean, you can work with this as well, but whatever makes more sense to you. Okay. Yeah. Okay. Okay. Yeah. Yeah. No change in the mid, no change in the low, right? Because we are moving towards the next one, so everything remains the same. Okay. Yeah, it will keep going. So that condition met. Let's suppose the condition if the number is greater than.
So would this be like outside?
No, it will be fine. So what's going to happen? No, no, no. So this is all inside the while loop. So it's keep running until this condition is met. So you are fine. So the next condition will be if the yeah the number is greater than mid. What happens then? Mm-hmm. Mid plus one, right? You're moving the low to the next one, right? And then it keeps going. And if it hits the condition, low is less than equal to high, it will come out. Otherwise, it's going to return the value. Yeah, towards the end, yeah, you can say -1 or not found. Okay, that's good. Thank you. See, wasn't that hard? Yeah. You guys see any questions on the algorithm? Okay. Um, you can, but it's not going to earn you any points because when somebody asks you the question, they are actually asking you your deeper understanding. How would you do your includes and all those things are additions. In actual code, in production code, yes, you are not going to write this. I have never written a binary search in my life, right? But I understand it, and that's what they're looking for. Do you understand how this is working? How does the sort work? I know you will use JavaScript.sort and it does it, but do you actually know what's going behind the scene? That's what they're looking for, a deeper understanding. Okay? Because if you're able to solve this without using includes and all that stuff, this means you have good analytical skills and you should be able to solve some of the problems. Okay? Now, there's a less chance anybody is going to ask you to write the binary search algorithm, but what will happen is they're going to formulate the questions where you will have to kind of use this algorithm. For example, the endpoint and the starting point, right? Um, those are widely used. If you go on LeetCode or HackerRank and solve some issues, you will come across some solutions where you have to search through an array, you have to do some kind of calculation. The good point would be that you use two pointers, like you have a starting point and an end point, and you divide by two and kind of come to closer and find that element. Okay, they were worded differently, but the bottom line is the algorithm is kind of going to look similar to this one. This is a very simple case. Usually they word it, add few more stuff to it, add few more questions, and you can look up on LeetCode. and eventually this would be the goal. But the understanding is that you have two pointers, they're coming to the midpoint and trying to search that number. That's what the main point of this is. Okay? Any other questions before we move on? Yes.
So during the interview, should we avoid
Yes. Yes. Please avoid. Yes. Especially if the company says, oh, you walk in and they're like, yeah, you can use any language you want. This is the indication that the person who's looking at the code might not know JavaScript. They might know Java. Or they know JavaScript, they don't know Java, right? But what they understand is anybody can understand this logic. So if you say dot include or something, you're like, well, what if I'm writing this code in Java? That's not going to work in Java. Yeah. But this logic can be translated to any language that you want, right? Why? It's using a while loop, if statement, for loop. Every language has that. But not every language has includes or whatever those other things are. So yeah, try to avoid them. Okay, that's what they're looking for. Okay, any other questions? All right, coming to the what is the efficiency of this algorithm? Okay, um, let me show you a nice graph over here, and I'll send this link also. It's a really good if you're going for interviews. Kind of keep this in mind. Okay, so we looked at big O of n, right? So if you draw it on a graph, this is how it is. So this is your time complexity, how much time it will require, and then how many number of elements are there. So n and q. Okay, so if you look at the linear search, the more elements you have, the higher the time cube goes up. Right? Eventually, it's going to become more and more inefficient. Okay. Now, what binary search comes under log n. Of course, there are mathematical calculations. We don't have to worry about those things, right? But you can estimate any algorithm that kind of follows this pattern. Any algorithm that is dividing the array into half, you can safely say it is of a big O notation of log n. Okay, doesn't have to be exactly binary search. Any algorithm you're trying to solve something and you come to a conclusion where you have two pointers, you're dividing the data set into half, then trying to search for it, then dividing in half and dividing in a half, you are basically doing binary search, and the efficiency for that is log n. Okay, just remember that, right? So anything, any code that you write that is kind of closer to this algorithm, the efficiency is log n. And if you look at the graph, this is a more visualization, and it helps me to understand how efficient this is. So you can see as the number of elements grow, the time is kind of growing less and less and less. At some point, well, it's not going to become constant because it's like an infinite graph. If you remember from your algebra, or not algebra, what's it? Calculus, right? It's going to go on and on and on forever, but the time is not reaching as high as this. So that's why binary search is considered one of the highly efficient search algorithms, right? What is the downside? It's not actually a downside. The thing is, your array has to be sorted, right? That's what we determine. So the question is, wouldn't it become inefficient if I have to sort the array and then do a search? It will not. The cost of sorting the array and then doing a binary search is still a lot less than having a linear search. Okay? This algorithm is still efficient. If you use a sorting algorithm that is highly efficient and then do a binary search, the cost of that is still going to be significantly less than using a linear search every single time. Okay? The only thing to note is you're going to use an efficient sorting algorithm, and there are highly efficient sorting algorithms. You can use that, sort the array, and then do a binary search. It is still going to be more efficient than linear search over here. Okay, that's why binary search is more preferred. Yes. Yeah. Yes. No. Log n is considering the array is already sorted. This graph doesn't it's not even thinking that the array is not sorted. Yes. Yeah. But I was saying the argument for that is what happens if my array is not sorted, right? Then yeah, the algorithm kind of changes a little bit. You will add some more because you will add the time complexity of your sorting as well, and then your binary search. But even both of those combined is going to be more efficient than just doing the simple linear search. Okay. Now, when it comes to big O, these are the most notable ones, and any algorithm that you write, I'm 100% confident is going to fall under any one of them. It's either going to be ON, inefficient, either it's going to be log n log n, or n squared, right? We'll look at n squared also um, when we're doing sorting, okay? So these are like five. So it's safe to say if you remember these five notations, and if somebody asks you that what do you think your algorithm is, it's going to be one of these. Okay? So it's a good graph to remember when you're writing code and when you're answering, because it's definitely going to fall under one of these. Okay? 0, 1, it's not going to happen. This is probably like an ideal case. It does not matter what you input, the time it takes the same time. It's like the ideal condition. I'm not sure if there's an algorithm that kind of reaches that, but it's over there. This means that you given any number of elements, million, 2 million, 5 million, billion elements, it's always going to take the same time to perform. It's kind of unlikely right now. Okay? But that's what O1 means. All right, so we looked at two algorithms, linear, which is ON, inefficient. Then we look at binary search, which requires some sorting. But if it is sorted, it is going to take log n. Again, this is the worst case, right? Remember, the worst case in binary search would be if you're trying to find the last element, right? But we found out that still it takes half or less than steps to even find this number over here. Okay? And it's the same thing if we have million rows, right? Million would be downsided to 500, then 500 would be down to 250, 250 to 175, and eventually it's going to come down to the last element that you're trying to find. But it keeps dividing that array, so it's still going to be more efficient than going through each one of the elements. Okay? The only thing to remember, the array has to be sorted if you're using binary search. Okay? And then it's still more efficient to sort that array and then use binary search versus skipping binary search and just using linear search. That is still not going to be efficient. Okay? All right, any questions? Good? All right, let's look at just one more sorting algorithm and then we'll end the class. We'll take a look at the easy one. Okay? So these are searching algorithm. The next one is sorting algorithm. What does sort mean? That you get an array where the numbers are not in order and you go ahead and sort them. All right? Let's see, for example, let me bring this up. Okay. So you have these numbers in front of you. Right? Write this down on paper. Just take 5 minutes and sort them as you would sort them. So I have 3, 44, 38, 5, 47, 15, 36. On paper, just sort them out and come up with these 10, 15 elements there. And then we'll see how do we do it in code. So I have 3.
10? Good. Okay, so 38, let's see, 47. 47, what is it? 44, 47, 46, 47, 48.
Similar conclusion. I made a few mistakes. So how did we? How did you guys search this? For example, how I was searching, I'm scanning the numbers. I'm like, okay, from this three, is there anything less than three? Yeah, two. Okay, so this is the smallest, and I put two. Then I looked at three, four. The next one, I started here and I say five, and then I just scanned the whole thing and said if there's anything less than five, doesn't look like. What's the next one? After five, I said looks like 15. Try to find something 15. Nope. So 15. The next one I saw was 19. Okay. And then let's say 38. Is there anything less than 38? 36. Less than 36, 27. 26. There's 19. So 19 comes first. So I'm picking one number and kind of seeing if there's anything less than it. How did you guys do it? Anybody who did a little bit differently? Yes. Eric.
The way I was searching for it, like the first numbers.
The what?
Like after the single digits, I scanned through and I saw 15 had a 1.
Yes.
So I scanned through all of them to see if there
Oh.
was another 1.
Okay.
And I found 15 and 19 and put them together. Same thing with the next one. So it'd be 2 and 2 and then 6, 7.
Oh, wow.
So I was scanning the first number and then the second number afterwards.
Okay. Wow. Haven't heard that one. Yeah. Anybody different from the first two solutions?
Basically looking at the height of the bars.
Yeah. Oh, looking at the height of the bars. Oh, that's interesting. Maybe should have removed the bars. Okay. Other than looking at the height of the bars, looking at the numbers. So my case was I'm picking one number and kind of searching through it. Eric was looking at the first digit and then picking those numbers, kind of collecting them together. Anybody else any different? Looking at the bars. Okay, let's say bars was the any other than the bars and the two method that I spoke. Anybody else a little bit different? What did you use? How did you do it? You are sorting them first? Right, that's the purpose. You have to sort them. How are you sorting them? No. Okay, so this was not the code. She's on the next level anyway. We'll come to that. I was talking how we as humans would sort these numbers. Okay, so there are techniques, and this is how the sorting techniques came about. And how do you tell the computer to do the same thing? Right? We'll start with the most inefficient one, of course, and then we'll see how they grew. The most inefficient ones are a lot easier to understand and a lot easier to code. When we get to, I won't cover the more complex one today, but the more complex one you will see are as humans is difficult for us to understand, but it's very easy for the computer to actually do them. Right? That's what they came about. The ones that we think are easier, for example, picking one and doing this is actually very inefficient for computers. Right? And why? Because the computer is going to pick one and then it's going to scan the whole array and then try to find out if there's a number that is less than 3. Okay? 2 it is, so it's going to say, oh, 2 is the less one. Okay, so let's move 2 at the beginning. And then it's going to scan the whole array after that and see, it's going to pick the next one and see, is there any number less than 44? Yeah, this is, so it's going to say this one. And then it's going to sort everything together. Let me show you how this one works. This is the only one we'll cover today. Okay? So we start with the array starts with the first one. The algorithm says, okay, 3, the starting of the array 3 is going to determine that that's the smallest. That's the assumption it will go with. And then it's going to pick that number and then going to compare each one, everything after that until the end of the array and try to find out if there's a number that is less than 3. Okay, so it picks up 4, No, keeps going forward to the next one. 38 less than 3, no, it's good. Then it goes to 5, no, keeps going. 47, keeps going. 15, oh, I'm not too fast. Oh, I'm picking the wrong one, sorry, this one, okay? It goes to 26, it went to 36 also, okay? Still, then it comes to 2. So it compares and says, okay, 3 is greater than 2. This means that there's a number that is smaller than 3 as well. So what is it going to do? It's going to swap those two numbers. So it's going to swap these two. Oh, it's going to swap eventually. It's going to say now my smallest number is 2. I still have long ways to go, like this part of the array is left. So I need to find out if there's anything less than 2. Okay, so it checks 46, 44, 4, 19, 50, 48, no. It's at the end of the array and it has found out that there's a number that is the lowest, but it's somewhere in the middle. So I need to move this number to the beginning of the array. So it's going to go ahead and swap the first one and the second one over here. Okay? Now at this point it is 100% sure that the numbers over here are all sorted. Right now it's just one number, so we can't really see it. We'll see the next ones. Okay? Now it's going to start the loop again. This time it's going to start from here, the next one. It's going to assume that 44 is the smallest, and it's going to compare 44 to every single one of these and try to find out if there's a number that is less than, which is the minimum for the remaining array. Okay, so 44 to 38, it is less than. So 38 is the smallest number now. Okay, and the reason is it doesn't know what is coming. Right now, what it knows is that there's a number which I have compared, and this is the smaller one. So 38 is going to be my new minimum for now. Okay, it compares to 5, finds the value, so it says, okay, now 5 is the minimum because it's less than 38. Okay, now it's going to compare 5 with the rest of the array. So it's going to say 47, okay, 15, fine. So keep going, 36, 26, comes over here, 3, right? 3 is less than 5, so it's going to say now 3 is my minimum. Okay, I still have these numbers to go through, so there might be a number that is less than this, so I'm going to keep continuing that. Okay, so it will go to 46, 44, 19, 50, 48, end of the array. There's no more elements, so it's going to swap this number with this one, the second one. Okay, it's going to swap. Why is it?
Why are you swapping right away? What's going on?
Right, so it's not sorting right away because this is an inefficient algorithm, so that's why it's not. This is how the algorithm is. It's called selection sort. Okay, why is it not doing it? Yes, there are different sorting algorithms. There are like a lot more algorithms that do it more efficiently. The one that we are looking at is called selection sort, and this is how it works. So if somebody says, how does selection sort work? This is how it works. It picks the first number, compares it to the rest of the array, and then brings the smallest one to the beginning. Okay, of course, this is, you guys can already see this is a little bit inefficient because it has to pick the first one, go through the array, come back, and then go through the array again, and keep doing it until the whole array is sorted. So now 38 would be, it will say 38 is the smallest assumption. Why? Everything before 38 has to be sorted. Otherwise, it wouldn't have been working. Okay, so it's going to go ahead, find the smallest one, 5. Keep going, 4. Smallest now. Keep going, and end of the array. So it's going to solve 4 and 38. Okay, so now everything until over here is sorted, right? Luckily 5 is sorted, but we don't know that. The algorithm doesn't know that, right? It will go through the whole step. It has no idea if this is the smallest. We can look at it and we can say, oh, it's small, but the algorithm has no idea, right? It's going to pick 5 and it's going to compare every single one of them and find out, oh, it was actually sorted, so it's going to do nothing. Okay, it's going to move on to 47. Compare this, 15, smaller, yes. This is the new minimum. Keep going. Try to find if there's anything smaller. Nope. We're going to switch 47 and 5. Okay. Start 47. Compare 44. Okay, that's the new minimum. Oh, 26 is the new minimum. keep going. 19, this is going to be the new minimum, and then swap these two. Okay? It's going to keep doing this until it comes to this or the end of the array. Okay? So what is this doing? This is a little bit more closer to, it's more intuitive, as in, as I said, a lot of people kind of use this selection sort when you tell them to sort something. Okay? Highly inefficient. You can see why it is inefficient. It has no idea if the array is sorted or not. It will keep going and doing the same thing over and over and over again until you reach the end of the array. Yes.
So that's probably
Yes. We'll come to that. So, any questions on the logic of how this is working? Does everybody understand how this is called selection sort. Okay? It selects a number and then compares the number to the whole array and tries to find out if there is a number that is less than that number. Okay? And then it picks the next one. Does the same thing again. It picks the next one, then does the same thing again. So it's selecting a number and saying that this is the minimum until it finds a number that is less than that. Okay? Alright. You're not going to write code or anything, but how many for loops do you think this is taking? So it's picking one number, comparing, and then another number, then comparing. Then one, then one. How many? No, how many for loops would you write? Not the number of for loops, not the number of steps. How many for loops are you going to write in your code? You say one? Why two? Why would you need two? How can you do this in one? So,
Oh yeah, I have to. Yeah, the first loop is going to be outer loop, and then
yes, excellent. So I'm going to have two loops. The first one, as she's saying, going to be an outer loop and an inner loop. So basically the code would be for one to something and then another for loop. Again, why? The reason is I'm picking one and then I'm going through the whole array. So you need a for loop to go through the whole array, and then you have to come back over here and do the same thing. So you need two for loops for this one. Okay, one for loop that is controlling the number that you have identified, and the next loop that goes through the whole array and comes back. Then the outer loop goes back again, outer loop then goes back again. So you need two loops over here. Okay, we'll look at the code. Exercise would be go back, look at the solution. But the main point is it's going to be using two for loops, one outer and one inner. Okay? The more number of for loops you have, the more inefficient your solution is. That's clear. Okay? And the reason is, remember, if you have a for loop, that's how many steps it's taking. Our linear search had one for loop and we said it's on. If you have two for loops, how much do you think it's taking? It's going to run the outer loop n times and the inner loop n times again. So n into n. It's going to be n squared. So it's running n squared times the same thing. So if you have million arrays, if you have an array of size 1 million, this algorithm is going to take 1 million into 1 million times to complete the sorting. Why? Because there's a loop that runs 1 million times and there's a second loop that runs 1 million times again. Okay? It runs less than a million, like 1 million minus 1 or something, but we are approximating the 1 or 2 will not make a difference. Okay? So the more number of for loops you have, nested for loops, not the number of for loops on the same line, the nested for loops. This is an outer loop. Within that you have another for loop. So this is called a nested for loop. The more number of nested for loops you have, the more inefficient the solution is. Okay? And how do you determine the big O or the O for nested loops? So the outer loop would be n multiplied by n multiplied by n, depending on how many loops you have. So if you have, for example, 3 nested for loops, for some reason, I have a for, and then I have another nested for loop doing something, and then I have another for loop doing something. This is n to the power 3. So n multiplied by n multiplied by n. Keep multiplying the number of nested loops you have. Okay? If n is bad, n squared is worse. N cube is worse. Again, I'm not making fun of somebody from the previous cohort, very brave enough to come and solve the problem. It had 5 nested loops. It had 5 nested loops. We were able to solve it, and he did a really great job. But this is how I explained them. Okay, the more number of nested for loops, the more inefficient the solution is. How many nested loops do you have? And he said they have like 5 nested loops. So that's a big no-no. Okay. So the more number of nested loops, again, I'm not talking about the loops on the same line or 2 separate loops. The more nested loops you have, the more inefficient the solution is. Okay, so if you look at the graph over here, n squared is crazy over here. You see, for just this small number of data set is going to take this much time to complete. Okay, now imagine n cube. N cube is not even there. It's going to be somewhere like over here. Like just a small one is going to take this much time to complete. Okay, so n to the power anything is a highly inefficient solution. Okay, so if you have 2 for loops in your algorithm, doesn't matter it's a sorting one or anything, right? You will come across, as you practice more lead code, you will come across some solution where you are using nested loops. Okay, 2 means you can make it better. Okay, but again, as your level, it's fine. Please go ahead and solve that with nested loops and then see if you can make it more efficient. Yes.
Yeah, it's the right, so it's more efficient. This solution,
The sorting one or your algorithm?
the different is
Yeah, the sorting one. Yes, yes. There are, of course, there are more efficient sorting algorithms. We'll take a look at next time. But of course, I'll send you this link. Yes, they are efficient. Of course, you cannot use this sorting algorithm at all in production and anywhere. Okay. For example, the JavaScript sort method. If you think it was using this, your code will still be running for now. It does not use. It uses a different sorting algorithm. So this was just a starting one that's more intuitive to us humans, but for computer, I was trying to say is highly inefficient. For us, it's easier to understand, right? When we get to the more efficient one, you will see it's for us humans, it's really hard to understand what's going on, but for computer, it's the most efficient algorithm ever. Okay, so we'll look at some more insert. It's called insertion sort. It's a little bit better, but not as better anyway. Okay, eventually we will look at quick sort. That's kind of considered one of the more efficient sorting algorithms. JavaScript, Java, they kind of use a mix of those sorting algorithms. We'll look at quick sort, but it's a little bit trickier to understand what's going on. And it kind of follows the same mechanism of little bit binary search. It has pivot and it does some sorting and all. We'll take a look at quick sort. But the next one we'll take a look next class is insertion sort. Not any better, but a little bit better than what we have over here. It's still considered inefficient. Okay. I'll share this one also. This is a good cheat sheet that I keep with me before I go in interviews. If you see selection sort, the one that we saw, it's inefficient even in a best case. It's inefficient if in an average case and also in the worst case. What would be the best case for selection sort? Everything is sorted, right? But do you see why? It will still go through the whole array because it has no idea it is sorted. If you give it a sorted list, it will still go through the same number of steps that it is going to go through if it was unsorted. That's why it's considered worse in every case. Now, why is it there? Yes, it's a starting point, it's more intuitive. That's the first algorithm somebody came up with. That's more natural. If I give you a solution, this is what you would come up with first, and then you will be like, oh my god, that's the really inefficient. I need to go back and improve on it. So that's why the other ones came up. So you see the other ones, these are more complex. We won't look into these. These are a little bit more complex ones. We will look at insertion sort. Still worse, but for the best case, it's still better than selection sort. But we won't use that. We will then look at quick sort. Okay, quick sort, again, you see it's still worse in the worst case, but it is still better for an average case. So if you have 1 million rows and the average is like 500,000 rows, it's still better than any one of these ones. So if you have 1 billion rows, the half of that quicksort will still work. Okay, I think Java they kind of use a mix of a few things. They use quicksort, and I think there's one more they use. So depending on how big your array is, JavaScript kind of juggles between and say, oh, I'm going to use quicksort for this one, I'm going to use this one for this one. Okay, because if you have a smaller array size, it's a waste if you're trying to use one of these ones because it takes a lot more. It's more efficient if it is more a larger data set. Of course, the coding for this one is a lot more complex, so that's why JavaScript kind of bundles those three. Okay. I will share these screenshots with you. Keep them with you when you're going through the interview. Just make sure you kind of look through it. Highly doubt unless you're interviewing for Google or Amazon, nobody's going to ask you about Redix or Google and Facebook are known to ask about these kind of questions. But if you're over here, it should be safe. I mean, even if you know bubble sort, insertion, selection, quick sort, should be good. Okay, as I said, a lot of people cannot even go through these. Again, I'm not saying you have to remember them. I have no idea what. I don't remember the code. What you need to know is how these work. If you look at the code, you should be able to understand. Oh, this is selection sort, and this is how selection sort works. Okay, and when I see the description, you should be able to translate that into code, just like Hannah did for binary search. All we did was go through the theory, and you guys were able to come up with the algorithm. That's what we're looking for. Okay, don't have to remember each one of them. All right, any questions? Yes.
Yeah, so it seems like the inefficiency gets worse the more nesting you have of
Yes.
algorithms. Is that the case with any type of nesting?
Any type of
If statement
Oh no, just for loops. Again, why for loops? Because for is execute. If it just executes one time. Remember the number of steps I said? If is going to execute one step. But if you have a for loop that goes up to 100 elements, it's executing 100 steps, not one step. So it's only with for or while also. Because anything that loops through, that adds more efficiency. And you will see if you have a list of elements, there's no other way other than using a for or a while loop. Now, how do you use them? That's the case where it comes in. But yes, the more nested you have, the more inefficient the solution is. All right, any other questions? All right, we'll take a break. We'll stop over here. Next class, we'll take a look at some more sorting algorithms and then data structures. Rest of the time, take lunch, work on your projects. That should be all for today. All right. Let me know if you have any questions.